Okay, overpotential effect. So, just like everything in chemistry 12/high school science or math, we kind of water things down a little bit and make them oversimplified. So, normally when I learn this in school, if you look on your data package, water has these little dashed lines that move it from there to just below zinc, and then up at the top, same thing, it gets moved up to just above chlorine. Okay? This is called the overpotential effect. Now, unless you're going to do a chemistry degree, you don't really need to know the ins and outs and why. I'm going to give you a quick little reason why, because there's a series of reasons. It's not just one thing. Okay? But basically, it's saying that instead of needing, shouldn't have moved it, say the voltage 0.82, it acts like it's more up here. You need a little bit more voltage. Okay? And the reason that is, depends on the cell that you're dealing with, but some of the factors are basically, if you form, one of the reasons is bubbles at an electrode. You don't have to write this down. I won't ask you these things, but this is just the background of why this is. All I care about is you know how to use it. So if you have bubbles at the electrode, it actually can act as a physical barrier to the electrons getting onto, here's your electrode, you got bubbles here with electrons built up, and you've got, say, sodium here trying to get to those electrons. It's actually a physical barrier, all right? So it results in this overpotential effect. Another reason is there's an activation energy to get the electrons off of something and onto something, okay? So there's an activation energy, just like we did in the first unit. To remove/gain electrons. Now, some electrodes can act as a catalyst in that sense, like platinum electrode can act as a catalyst sometimes, depending on the reaction. You don't need to, like, again, you don't need to know any of this. I will not test you on any of this. But they used to just tell me what overpotential effect, and they never gave you a reason why. These are just some of the reasons why. So the bubbles can act as a barrier, activation energy. So if you use different electrodes, you can lower that activation energy, and it allows the electrons to transfer a little easier. There's the movement of the ions through the medium, like the aqueous solution. Sometimes it'll be fast, sometimes it'll be slow. There'll be concentration gradients within the solution that can act as barriers or speed things up, slows things down. So movement of ions through solution. Essentially, and there's a couple other things as well. All of these add to this perceived increasing voltage that you need to move to get the cell to go, okay? So what it does is it results in water acting more like something up here, okay? Instead of, like when you're reading off, say, the oxidizing ability of water, you don't read it like it's here, you actually read it as if it's up here. But you still use this voltage. So we're just going to do an example question. You just have to know how to read the table, essentially. So, here we go. Predict the chemistry in an electrolytic cell with inert electrodes containing 1 molar solution of zinc chloride. Okay, it's a 1 molar solution of zinc chloride, so we got zinc ions, we have chloride ions, and we have water. Okay, and it's neutral. If I don't say anything, it's neutral. Okay. So the cathode, which is the reduction. And we'll write anode as well. Okay. So when we're looking for the cathode, we look on the left side of the column, highest. And we're looking between these three things. First of all, whatever, we'll just look it up. Here we go. So we've got zinc, chlorine, and water. Zinc, chlorine, and neutral water. Okay. So we're looking on the left side only. So I'm going to go down because I know where it is. Here's water, neutral water, and here's zinc. Which one gets reduced? The zinc, right? So water, normally it wants to be here because they list these in the voltage order, but its actual effect is down here. So zinc is actually above it and will be reduced before the water molecule will. Okay? So the cathode reaction is going to be zinc picking up 2 electrons. They don't what, sorry? Oh, I see what you're saying. Yeah, that. Yeah. And we form zinc solid. So that's the cathode reaction. Then you go to the anode. Oh, sorry, and we should write the E naught of the cell is negative 0.76. Okay. The anode reaction. So we're looking for water and chlorine. They're going to be up here. There's my neutral water here. Chlorine is right here. You can tell why they picked this one. So normally you would think water is what's going to be oxidized, but due to the overpotential effect, it actually acts up here. So the chlorine is actually going to be oxidized. Okay, so the chlorine gets oxidized to chlorine gas. So it's 2Cl minus chlorine gas plus 2 electrons. And the E naught, sorry, reduction potential, negative 1.36 volts. So when you add these two reactions together, the overall reaction is zinc plus 2 chlorine molecules gives me zinc solid and chlorine gas, and the cell potential is negative 2.12 volts. Okay? So all you have to do when you're doing something is account for the reduction potentials. All right? But the voltage you use is the same voltage that is in the data booklet. So if we were using this reaction here, we would use a voltage of 0.82. But you just pretend it's essentially up there. Okay? That's it for overpotential effect. Finish those questions. I'll post the